Hello and welcome to our CVPR 2021 presentation on the paper Student-Teacher Learning from Clean Inputs to Noisy Inputs. My name is Guanzhe. Consider the following setting. Suppose we have a teacher neural net that is pre-trained to classify clean images and it generalizes poorly on noisy images. Now suppose we have a student network with identical architecture that needs to classify noisy images and we need a way to train it well. The learning scheme which we consider in this paper utilizes the perceptual loss, i.e. the difference between the hidden features of the student and teacher networks. During training, we just add this perceptual loss to the base training loss, like cross entropy. There is a good number of experimental papers that apply the student-teacher learning technique in different problem settings. However, theoretical understanding of why it works remains elusive. There are only 3 theory papers whose setting is somewhat related to ours. One only studies kernel-based models, not neural nets. One studies label-based distillation, not feature-based. And one only considers the training dynamics of a student, not its generalization. Therefore, the following problem still remains open. When, why, and how does feature-based student-teacher learning work for neural nets? This is the problem we study. Let's move on to our findings. We focus on the student first. Consider this question. Should we train the student to convergence and would it generalize well? To theoretically answer this question, we have the following setup. Let the student and teacher be 2-layer linear neural nets, so they are just the product of 2 matrices. Let the baseline training loss be MSE, so our student-teacher training loss is MSE plus the perceptual loss. Note that we assume the teacher network attains minimal error on the clean version of the training data. In this setting, we prove that if you train the student to convergence, it's just going to recover the baseline or a solution very close to it, so it won't generalize any better. Due to time limitations, I won't cover every detail in our theorem here, but one thing I want to mention is that in the over-parameterized regime, where multiple solutions exist for both the baseline and student-teacher learning, we let gradient flow, the continuous version of gradient descent, be the optimizer and assume small norm initialization. This is close to common practice. Now we shift our focus to the teacher network. A natural question is, when do we need a more knowledgeable teacher network for the trained student to generalize better than the baseline? Part 1 of the answer is when we have more training samples for the student. To verify this claim, we carry out experiments on the CIFAR-10 dataset by using resident 18 to do image classification. We fix every parameter and only vary the number of training samples for the student and teacher. We let the number of samples to pre-train the teacher be the proxy for how knowledgeable it is. In the plot on the right, the region shaded in green is the region where the student-teacher learning beats baseline learning. We indeed observe that when the number of training samples for the student increases, we also need the teacher to be pre-trained with more samples for us to stay in the ideal working regime. We also found that when the task difficulty for the student increases, the teacher also needs to be more knowledgeable. We use noise level as the proxy for task difficulty, and verification of this claim is done in a very similar fashion to that of the previous claim. Please refer to our paper for more detail. Our third point concerns the following question. Is a teacher with low test error on his task necessarily a good teacher, and does it always teach a generalizing student? Our answer is not necessarily. The simpler the teacher's hidden neurons are, the lower the sample complexity of training a generalizing student. Due to time limitations, I won't cover the full theorem here, but instead give you some intuition on our results. Let's again assume that the teacher and student are 2-layer linear neural nets. Suppose for the teacher at the top, its hidden neurons are influenced by every entry in the input vector, so the neuron's output or the hidden features are complex functions of the input. When we use the perceptual loss to train the student, we're asking the corresponding hidden neuron of the student to learn this complex function, and the sample complexity can be high to learn a generalizing solution. Now let's assume that each neuron of the teacher is influenced by very few entries of the input. In the picture, it's only 2. Then the hidden features are very simple functions of the input. It follows that it takes fewer samples than before to train a generalizing student. Notice that even though each hidden neuron of the teacher is simple, as long as there are many of them, the overall function of the teacher network is still very complex. The idea of knowledge decomposition comes from this observation. In conclusion, we have 3 messages in this paper. 1. Training the student to minimum loss or convergence is harmful to its generalization. 2. A knowledgeable teacher is generally preferred, although there are limitations. 3. Better knowledge decomposition leads to better knowledge transfer. Thank you for listening.